technologies. One of the areas that I've been focusing on has been traffic management, traffic engineering, and network planning. And what I'm going to try and do this morning is to give you, I guess, the best practice or the state of the art on network planning and engineering. I've grayed out and traffic engineering, and the reason that I've grayed it out is because when I put it all together, I actually had too much content. And I don't think I'm going to get that far, even though I thinned out the upfront bit as much as I thought was right for the audience, if you like. But let's see how it goes. If I get time, I can go on to some of that. If I don't, then there's a placeholder there. And if you think it's interesting enough, I'd be very happy to do that as a follow-on session at some future time. Okay. So to start with, what do we mean by network planning and traffic engineering? So really, I think if you look at the way that many people capacity plan their networks today, they do it on a pretty simple basis, or looking at link statistics, looking at the utilization of those link statistics, upgrading when they hit threshold exceptions. It's an approach that's been around for a long time, but it's got some shortcomings. And I think in general, trend-wise, what we're seeing is a recognition of those shortcomings and a move away from, if you like, the one guy that deals with capacity planning, separate from the engineering team, separate from the operations team, to a more unified approach where planning and engineering and operations are linked. Specifically, I think that's happening in sort of two stages. The first one is planning and engineering becoming far more integrated, and then also looking at how that can move into operations. But also seeing that capacity planning and network planning is becoming more systemized than it was, rather than being once a month producing a report saying, okay, I need to upgrade links X, Y, and Z, being something that's done in much more real time. That may be no good to say at the end of the month, I need to upgrade this link, if it's going to take 2 months to do it, and actually the increase in traffic demand is happening at a much quicker rate. So I think there's no reason, really, why those sort of approaches need to be done in that sort of time frame, and why they can't be much more real time. But capacity planning can sound dull, can sound boring. Why is it important? Well, I think there's one key thing that is often missed when people consider delivery of SLAs in IP MPLS networks. If you consider ATM networks, in ATM networks, you had mechanisms implicitly built in and set by default by most of the manufacturers that would guarantee that at any point in the network, for those services that were important, which you'd put on a CBRVC or so on, that there was something that managed the ratio of the offered load, the offered traffic load, and the available capacity. And that one thing is fundamentally the most important thing for managing your end-to-end SLAs. If you get that ratio wrong, your offered load over whatever time you're measuring it exceeds your available capacity, you're not going to get the service that you expect. In IP MPLS, we don't have that. You might consider that MPLS traffic engineering gives you that, but it doesn't. MPLS traffic engineering gives you a capability to be able to steer aggregates of traffic, but some of those other elements that were there with ATM designed, if you like, from the bottom up, aren't generally used in the same way with IP MPLS. You don't condition per tunnel, generally at the edge of the network. A tunnel has no concept of average rate and burst. Typically, we don't use traffic engineering for admission control today. We don't reject. It's actually very rare to have a situation where you reject a connection. So it's far more used for either for resiliency reasons or for steering traffic, off paths that may be congested. So how do we manage that problem in IP MPLS? That fundamental problem of managing the offered load versus the available capacity. You've got diffserv, but all diffserv gives you is the capability to do that on a per-class basis. It doesn't manage the problem. You've got traffic engineering. Well, that can allow you to manage that problem, but it doesn't allow you really to understand what sort of order of magnitude the problem is. It may allow you to move traffic off a congested path to another path, but up front you've got to understand, why is that path congested in the first place, and is traffic engineering the right solution to resolve that congestion? So, summing that up, actually capacity planning is one of the key components of ensuring that you can deliver the services that you expect across your network. In ACM, that was not the case. You could almost ignore capacity planning and allow, by default, the if you like, the exceptions generated by your NMS to trigger you to do network upgrades, and know that you weren't jeopardizing your services in the meantime. So, trying to bring that all together then and come up with a sort of holistic methodology for capacity planning that goes beyond just looking at per link statistics and upgrading when you get to exceptions. So I've put up a process here, and it looks pretty, well, it could look pretty complicated, but actually it's not. 6 steps I've shown. The first 3 steps, if you like, are methodology. The second 3 steps are application of that methodology. So, step 1 is really understanding your traffic demand matrix, and I'm going to talk about that in a bit more detail. And the traffic demand matrix is, something which gives you context beyond just link utilization. Second step is then understanding that within the network, for services that are important, you never want to run in a congested state. But what does congestion mean? Congestion over what time frame? Over 5 minutes, over 10 minutes, over half an hour? Well, typically it's congestion over milliseconds, because that's what matters. You don't want to get bursts of congestion where you get packet loss, delay, and so on. But how can you manage that microseconds worth, that queuing over sort of microsecond time frames, when actually what you're looking at in the network are averages over 5 minutes when you measure utilization? Well, you do that by understanding effectively the burst characteristic of traffic and how much you need to provision, how much traffic you need to provision in order to meet a certain SLA target. So that's what I'm calling, if you like, the over-provisioning factors, and I'll talk about that in a bit more detail. Step 3 is then doing something intelligent with that. If you understand your traffic, where it's going to and where it's going from, you understand how much capacity you need to put in to actually meet the targets you're looking for, then the third stage is actually understanding how that traffic behaves on your network. Understanding how it behaves, how the IGP routing works, how multicast routing works, how BGP failover on peering works, taking all those factors into account to then work out your traffic routing. Perhaps looking at failure cases, looking at growth scenarios, and so on. Step 4, well, if you know all that, you can then choose whether you want to do something better than you're doing today. Perhaps you might want to deploy MPLS-TE, perhaps you might want to tune your IGP metrics, perhaps you want to put in another link. Step 5 is then making those changes. And step 6 is then, I've shown here, is the operational context of that. And I'm going to explain a bit more how some about what I'm talking about can actually relate to operations, where today I think, they tend to be separate functions. Okay. So to start with, step 1, the traffic demand matrix. So it's typical today to capacity plan based upon link statistics. You just look at the utilization of a link over 5 minutes, 10 minutes, 15 minutes, whatever it may be. The shortcoming in just looking at the utilization of link statistics is, if you want to understand growth, link statistics aren't enough, because it might be that you have growth in a traffic demand from London to Frankfurt, which happens to be crossing one link, but you have a number of other demands that are also crossing that link which aren't growing. So if you look at the growth of, if you just model the growth of a traffic on a link, it may not give you the right context. Also, if you're trying to plan for failure cases, it's no good just looking at the utilization on one link, because there may be a number of demands crossing that link, and in the failure of that link, those demands may be routed on different paths. So in understanding really what happens in failure cases, you actually need to know the traffic demands. That is, the aggregated demands of traffic from one part of the network to another part of the network, which can be, it can be right out at the edge to the edge. It could be, you might be more focused just on, if you like, an inner demand matrix if you're just focusing on the core. So when you look at optimal network engineering, i.e. making sure you can hit your SLA targets and making sure that you haven't got too much capacity in the network, then you really need to understand your traffic demand matrix. Two types of traffic demand matrix that I'll point out. One is internal, so this is really what you can think of as POP to POP, or access router to access router, or core router to core router. That's important for understanding what happens, obviously, inside your network. Excuse me. But also there's the external traffic matrix, which is from things internal to your network to external AS. And the reason that's important is because in failings of peering connections, it's important to understand the behavior of that, i.e., it's which AS traffic is then going to be coming in from going out of when you've had a failure of one peering. And the information that you need to understand to model that is actually different from the information you need to understand to model the internal failures. So traffic matrix sounds interesting, but how do you get it? There's been an evolution really of traffic matrix information and how you derive it. So starting point, I think Robert's left, but starting point really was to try and see, okay, can we derive our traffic matrix natively from the network? So we just get the traffic matrix information directly from our routers. It's a great idea, and a number of approaches for achieving that. I think in reality, and I'll touch on it in a couple of slides, none of them actually today are able to provide you with that complete traffic matrix. And there can be a number of reasons for that, either inaccuracies with certain approaches, or the fact that approaches aren't universally deployed, issues like that. But I would say in general, probably in the networks we look at, maybe 30% of them we can use, if you like, a directly derived traffic matrix from the network. So, and I'll touch on some of the issues in another slide. So that's one approach. So then what we had after that, when it was obvious that, I think in the early days of some of those capabilities, vendors didn't have the functionality, they weren't actually out there deployed, so there was a need to come up with another approach for actually understanding the traffic matrices. And that's where demand estimation came about. And demand estimation, the idea behind demand estimation is you look at the information that you do have in the network and you run a mathematical process to try and then work out what that traffic matrix is. And demand estimation I'll touch on again in a slide. I've got a slide on that. It's accurate in some cases, but in a large number of cases it has inaccuracies. So generally it's not good enough on its own. It does provide you extra information, but it's not good enough on its own. So where we're really at today is to use an approach that's a hybrid of both of those. And that's using a demand estimation model from linked statistics, but increasing the accuracy of that by using specific information from the network from direct measurement, which could be from NetFlow or other approaches. So let's just touch on those in a bit more detail. So the first one was the direct measurement approach. So this is, relying upon the network to actually give you the traffic matrix information. And there are different ways of doing that. We've got approaches that use, just reporting flow data from the network. NetFlow is one example. NetFlow today, typically version 5 is what's most widely deployed, but actually deriving a traffic matrix in version 5 is a very complicated or a very resource-intensive task. It takes a lot of time aggregating that flow information, that individual flow information into aggregates that make sense in the network. Version 9, so Cisco version 9 introduced the concept of aggregating traffic matrices based upon BGP next hops. Well, if you aggregate traffic based upon the BGP next hop it's going to, that implicitly gives you the traffic matrix, if you like. But not widely deployed, only supported by Cisco. So, pardon? And Juniper. But not supported by some other vendors. But But again, limited deployment, very limited deployments today, and not generally deployed all around the edge of the network. So if it's not, then this isn't enough on its own. And then we get inaccuracies. So we've done a number of studies where we've looked at deployments where we know the traffic matrix. We've got some deterministic way of knowing what the traffic matrix is, where the traffic's coming from, where it's going to, and then applying these different approaches in order to understand the different accuracies of them. Actually what we find with NetFlow is that it's accurate within particular time frames, but taken over a longer time period, there are inaccuracies that creep in due to stats mismatches, due to different vendor implementations, and so on. There are other flow-based approaches. BGP policy accounting is probably the main one today, and this is where you aggregate traffic, you report statistics based upon which BGP next hop it's forwarded to. Typically, with BGP policy accounting, there isn't enough granularity of information in order to be able to report a traffic matrices. I think that's a shame, because actually, as an approach, that would have been a very efficient approach if that was usefully supported across all vendors. There have been other approaches in the past. One was called traffic matrix statistics, which Cisco did a long time ago, which actually was exactly what you needed at the time. It never gained any traction, and they've stopped doing it. So, what we see with the flow-based approaches is we don't have a consistent approach that we can really get the traffic matrix information from. So what about other approaches? Well, if you've deployed MPLS, with MPLS, a label switch path is implicitly an aggregate of traffic across the network. So, can we use that to derive the traffic matrix? Well, if you've got LDP, yes, potentially you can if you've deployed LDP. What are the issues we see with that? Well, one is that you've got an awful large number of measurements that you need to take from the network. And I think this goes back to the order of n squared issue that was discussed yesterday in the traffic engineering presentation. Same sort of issue. At every edge point, you've got to extract the data for the traffic matrix to every other edge point effectively. So if you've got n edge points, you've got an order of n squared. You've n squared measurements that you need to make. So need to take. No, you can have, yes, but you don't have by default. So RSVPTE, and also we see inconsistencies in vendor implementations. Some vendors don't report at the first hop what the traffic matrix is, which is actually quite an issue if you're trying to poll it from that first hop. RSVPTE. Well, again, I think we go back to more deployment issues with RSVPTE. A full mesh is, difficult to deploy. Order of n squared issue, polling of those n squared tunnels, and again, inconsistencies in implementations. So I think in reality, while we'd like to be able to use a direct measurement approach for getting the traffic matrix from the network, in practice, it's the minority of cases where that's possible. So, if we can't do that on its own, what other approaches are there? Well, that's where we get to demand estimation. So, what is the problem that demand estimation is trying to solve? Well, if you consider this case, if you consider that we've got a particular link on the network, we're showing here that one link. We know the utilization on that link, but there are a number of traffic demands that are crossing that link. From that link utilization, can we somehow deduce what those individual traffic demands are? That's the problem that demand estimation tries to solve. And there are a number of different approaches to demand estimation. The most commonly used is what's called a gravity model, and I'll go on to that in the next slide. So if you consider those particular two demands that I was showing, then you actually end up with a range of possible solutions. If you know your utilization on the link is 6 meg, then the sum of those two demands is 6 meg, and you've effectively got a range of possible solutions for how much one demand can be versus the other demand. So how do you actually, how from that do you pick a particular solution to that problem? Well, what the gravity model does is it says, okay, well, what I'm going to assume is that if location B is pulling 30% of my network traffic, 30% of the aggregate traffic in the network out. Point C is pulling 50% out. Then I'm going to split the demands on that link in proportion, effectively, to how much those two sites are syncing on aggregate. So, you know, the simple way of putting it would be that if you've got one site that's syncing a huge amount of traffic, one site that's syncing less, and there's a link that's connecting to those two sites, you would assume that the utilization on that link is, in majority, made up of the traffic that's going to the biggest sink. Okay, so sounds simple enough, but how accurate is it? Well, we've done a couple of studies on this, and the left-hand graph is showing a comparison between the actual measurement. This is where we know actually what the demand utilization is. And the left-hand chart is showing actual utilization versus estimated utilization. So if we actually know the demands, and then we can also run an estimation, we can compare how effective the estimation approach is. And what you see is that, you know, ideally we want everything lined up with a diagonal line, i.e. what you're estimating is what you're getting. Now, as you can see, we've got a bit of a spread, so there is inaccuracy in there. But that inaccuracy is visible when you're trying to plan networks for working case. If you're focused on planning your network for failure case, then a lot of those inaccuracies go away, because, you know, with demand estimation, it may be that you've made an assumption that traffic's following one path. In practice, the demand is over another path, perhaps another equal cost path, and you've got the understanding and the split wrong. But if you're looking at failure case, the number of options goes down, and what you see in modeling failure case is that demand estimation becomes, you know, significantly more accurate. And so if failure case modeling is what you're after, demand estimation is generally an accurate approach. This slide was kind of showing that issue with demand estimation, that you don't actually know when you've got multiple demands over a particular link. You may estimate, you know, the proportion of one demand relative to another wrong, especially where you have multiple parallel links. But when you have a failure, in this case, if the San Jose to IOD link fails, you'll be going via Chicago, and you know, everything will be going via Chicago. And so for failure cases, the impact of estimation is far more accurate. But okay, so we've said that direct measurement doesn't solve our problem. Demand estimation perhaps solves our problem if we're looking at failure cases. If you're looking at working case, you know, what else can you do? Well, if you have some network information, some direct information that you can get from the network, which could be from NetFlow, it could be MPLS traffic engineering statistics, it could be MPLS LDP statistics, it could be just information like, you know, we know there's no traffic going from site A to site B, for example. Then if you run a regression process against an estimate used with demand estimation, you can actually significantly increase the accuracy of that demand estimation process. So effectively, it's combining the two things. If you combine demand estimation with direct data from the network, so you're using the direct data to make the demand estimation more accurate, you actually don't need very much information or specific measured demands in order to make that very much more accurate. And that's what we're showing here. And again, this was done on a network where we knew the actual network traffic demands, so we were able then to understand from the direct information we were putting in for each piece of direct demand information we were putting in to improve the accuracy of the model, we were able to understand actually how accurate it was. And so this is showing what's here is defined as the measured relative error. And you can see that when we get down to around about, you know, 10 demands and greater of specific information we are putting in, then the accuracy of the demand estimation approach becomes very much more accurate. And so that's the point where we actually start getting into, you know, we've actually got a traffic matrix now that we can use both for failure case and working case. So, you know, what's the summary? I think 3 points to bring out. One is that actually when you look at the accuracy of data, the one thing that we've found to be very accurate is interface statistics, but doesn't give you the traffic matrix. Where it's collecting traffic matrix data direct from the network is challenging in deploying net flow, in deploying full measure T tunnels, in polling every single PE for your LSP stats, for example. But as it's convenient, as you can actually fit that into your operations, it does make sense to do that to improve your accuracy. But you don't necessarily have to do that across the board. And then by running a regression process, you can actually combine those two things and come up with an accurate picture. Sounds great, but do people actually do this in practice? Well, yes. This is a particular example of a large provider not too far away from here, who do they do topology discovery in real time. They take their LDP statistics every 30 minutes, so only really periodically, and that's where their space. They're not sampling all of their PEs every couple of minutes. They're just doing it periodically to increase accuracy. They're taking interface measurements, just interface utilization measurements every 2 minutes, and then running a regression process online in order to produce their traffic matrix. So they end up with an accurate traffic matrix for every 5 minutes. So I think I'll just kind of cover some of what I've already said. But in terms of approach, I think recommended approach, and if we want to try and keep it as simple as possible, I think what we typically kind of recommend is an incremental approach. So start off by collecting that information that you're already collecting, and then see how good that is. See whether it's good enough. If it's not, if that direct information is not good enough, then look at demand estimation. And again, we can work out how accurate the demand estimation information is, but it's an easy way to get traffic matrix data if it's accurate in your topology. If it's not, then look to increase the accuracy as you need to by adding specific data for regression so that you can run regression processes. Okay, so that was the starting point, which actually I would say is kind of an essential starting point, because if you don't know your traffic matrix with a level of accuracy, everything else is somewhat pointless. So next, if we know our traffic matrix, how much capacity do we have to put into the network in order to be able to support the SLAs we're trying to achieve? Well, if we're measuring, if we're doing our traffic matrix every 5 minutes or every 10 minutes or every 15 minutes, implicitly that is a measured average over that time period. So if you want to ensure that you're actually going to achieve the sort of SLAs that you want for that traffic, you need to be able to understand that for that measured average traffic, you've actually got sufficient capacity to be able to cope with the peaks, the peaks of burst that you see within much smaller time intervals. And to understand that, you have to understand what the relationship is between measured average and effectively bursts of traffic demands. Now, if we go back 7-8 years, effectively what you had was two sort of opposing theoretical arguments. One which was saying internet traffic is effectively Poisson, which, as voice would be. So the idea there being the more it gets aggregated, the less visibility you have of burst. And so, the higher the speed of links, the less, if you like, headroom you need to leave on that link in order to ensure that you can hit your SLA targets. The headroom for burst needs to be lower. Opposing approach is saying actually it's self-similar. What does that mean? Well, it means that in whatever time frame you look at the traffic over, it's always bursty. Whether you look at it over a 5-minute average, over a 5 millisecond average, or a 5-minute average, you're still seeing significant burst. Now, probably any of you here that have used MRTG to graph your link statistics over different time frames will probably say it's pretty obvious that it's not self-similar. On the other hand, it's actually not going to be Poisson, because it's really not a Poisson process. So the question then becomes, well, if we understand these are the two extremes, where are we in the middle of that? If you're at one extreme, you come up with a pretty catastrophic consequence. If you're in terms of how much capacity you need to put in the network, if you're in the other extreme, you may just not put enough capacity in the network. So we need something that's a bit more, I guess, a bit more practically useful. So I don't know if any of you know Thomas Telkamp. Thomas did a study, and this is an ongoing study we've been doing on a number of providers, but the first results were 2003. The results we've seen since then actually line up with the results in the initial study. And what was done in that study was, rather than to make assumptions about traffic arrival, about number of TCP sessions, about the round trip time between TCP sessions, and simulating individual end systems, if you like, in order to try and understand queuing behaviors, was to say, okay, well, if I do that, whatever I do when I do that, I'm making assumptions, and I'm making assumptions which invariably will always be invalid. And depending upon what assumption you make, you'll get a different answer comes out at the end, which is why you end up with these two opposing views. So rather than that, if what I do is I take a network and I actually sample the data from the network. So I take a trace of the packet arrivals and of the timestamp associated with those packet arrivals and the size of the packet. And if I'm doing that on a link that is significantly underutilized, then I've got a fair understanding that is that effectively gives me a traffic trace that I can then use. And if I take that from multiple places around the network, I can then take those traffic traces and I can aggregate those and then put them through a queuing simulator and then understand actually what behaviors I would expect to see on a real network based upon real traffic profiles. And so that's effectively what we did. And so from that, these are the results that come out of it. And this is one particular result that comes out of it. So what we're plotting here is what for the measured average utilization over 5 minutes, what the 99.9th percentile delay is for that traffic. So measured average utilization over 5 minutes, well, we can work that out because we know the actual packet trace. So we can deduce whatever measured average arrival you want for those packet traces. The percentile 99.9 queuing delay, so that means the delay for which 999 packets out of 1,000 is less than that point. How can we determine that? Well, by running these traces through a queuing simulator, we can simply understand what the queue occupancy is at any point in time. We know the traffic arrivals. We can actually determine the queue depths and so on. So in doing that, what do you see? Well, actually, what you see is that the traffic isn't quite Poisson, but it's very close to it. And the higher the bandwidth of the link, effectively, the greater the aggregation of flows on that link, the closer to Poisson it becomes. And so if it is something that approaches Poisson, what that means is we can actually make reasonable estimates of the amount of headroom we need to give traffic in order to achieve certain delay and SLA targets. And so what you see, in this case, I've shown two examples. I've shown 622 meg 1 gig. We've done the same thing, same thing up to 100 gig. And what you see is that basically, that graph which shows the measured average utilization versus the queuing delay, that graph creeps further to the right as the link speed goes up. And you can see here that, if I wanted to achieve for 999 packets out of 1,000, I wanted to make sure that they were experiencing at most 1 millisecond delay per hop or less. Then, okay, at 622 meg, I'm going to have to keep my 5-minute measured average utilization down below something like 80%. And if my link speed goes up to 1 gig, it creeps up to, something just below 90%. So this is something which, is still, I think it's a practical approach to the problem. Now, you might still say, okay, well, that's based upon one network. What if my network's different from that? Well, we have done this in several cases and seen similar results. But it's also a process that can be run, on any network in order to understand what that is. And it's actually pretty easy to run it, and it's pretty easy to reproduce it and to see what that is and how that changes over time. My PC has gone to sleep. Oh, there we go. So just another point to bring out about that is that also what I was talking about there is when we focus on one hop. So you might say, okay, well, that gives me 1 millisecond per one hop if I was getting that target. So if I was going over 10 hops, does that mean I'd expect my 99.9 percentile to be 10 milliseconds? Well, the answer's actually no in terms of what we've seen, because we've done this over successive levels of aggregation. And I think typically what you'd expect is that jitter is not additive, meaning if you expect to see a certain delay characteristic over one hop, you wouldn't expect the same packet to experience the same delay characteristic over the next hop. And so what we see is that if we take this particular example and look at the queuing over one hop, where the 99.9 percentile is 2 milliseconds, actually when you put it over two hops, two successive hops, it doesn't go up to 4 milliseconds, but it's actually 2.6 milliseconds. So actually what you see is that over successive hops, if you were considering the statistical delay of a single packet, you would not expect to experience, the worst case at each hop in the network. And so if you look at end-to-end planning, you can actually be, a little less conservative than you might otherwise be. Okay, so far we've got our traffic matrix. We understand how much, now how much capacity we might want to put in the network to hit a particular SLA target. What do we do with that? And so, in practice, you need some way of actually overlaying that traffic matrix on the network. You need to be able to allow for the routing of the network. You might want to focus on failure cases, what happens in particular failure scenarios, in link failures, in node failures, in SRLG failures. You might want to try and understand what happens if you change the physical topology, if you change the logical topology, and you may also have deployed diffserv and want to model what happens to one class versus another class. And so, that's where some form of simulation process sits in to actually take that demand matrix, put it on the topology, and run through those cases. So, just give you some examples. So, one might be, in this particular case, failure case planning. So, if we look at just individual link utilizations, and we might say, okay, when I achieve 50% utilization, I'm going to upgrade. On any link, I'm going to upgrade it. But as a rule, that only really focuses on what's happening on that link and doesn't look at the bigger picture. And so if you've got the traffic matrix information and you know your network topology, you can actually, if you run a simulation, you can then determine in failure cases what's actually going to happen. So you can look at the failure of each link, of each node, of each shared risk, and then actually say, what utilization would I expect on each of my links in those cases? And what I'm showing on that top view there is an aggregated view. So it's showing the highest utilization on any link caused by any of the failure cases that you're worried about. So it might be that, that one of those links is red because of a failure of a certain circuit, another link would be red because of a failure caused by another circuit. So it's, if you like, an aggregated view, the worst case analysis. Bottom slide then is showing, well, once you know that, you can then look in and see, okay, well, what is the element that's actually causing those worst case conditions? What is the element that's going to cause this particular link to be in some form of congestive state when I look at failures? And it might be that, it's another link which is undersized. It might be that you've got some shared risk. You've got, two fibers in the same duct, or it may be some other issue that you can solve. So once you've got that, then you can do your what-if analysis. That is understanding, if I put a new link in the network, what the effect of that will be. Or if I change the routing, what the effect of that will be. Also with this information, another, if you like, form of what-if analysis is growth analysis, which is actually saying, okay, well, that's what I've got today, but I understand that my traffic demand from here to here is going to increase, or I understand that my edge sales have gone up in Amsterdam by 40%, or my predictions are going up by 40%. What's the impact of that going to be on my traffic matrix? What's the impact of that going to be on my network? Understanding that, my sales cycle doesn't necessarily tie in with my capacity provisioning cycle. So, step 3 was the simulation. Step 4, the optimization. And I didn't think I was going to have time to do all the traffic engineering side of things. But what do we mean by optimization? Well, optimization, I think, covers two aspects. One is re-engineering the network. So perhaps putting a new link in where you didn't have one, perhaps putting a direct link in, perhaps upgrading a link. Traffic engineering, on the other hand, is, given a fixed network, is how you can somehow engineer that traffic on that fixed network to give you a better overall effect. Now, clearly, they're both linked. But in order to understand which of those you need to do, or which of those are most effective, you've really got to have done all the preceding steps. You can't really make intelligent decisions about those things if you don't understand your traffic matrix and how that relates to your network. So when you consider, different approaches for traffic engineering, approaches for tunnel placement, whether you want to tweak metrics, you've really got to understand upfront what your traffic matrix data is. So then when we look at the different approaches you can make for optimization, if you've got that data, you can actually make intelligent choices about, what approach you might need to take. So, the first is you've got to decide what your optimization objective is. Are you optimizing for working case? Are you optimizing for failure case? That's a really basic but very important upfront decision, because the answer you make will be very different depending upon which approach you focus on. Then you've got questions about what actual technical approach you're going to take to solve the problem. IGP metric-based traffic engineering. So this is something that a few years ago was sort of considered not feasible, but I think there are public statements by BT today showing that they do that actually effectively on an ongoing basis. So that's a potential approach. MPLS traffic engineering is another approach. But with either of those, then you have choices about whether you're going to do them strategically or tactically. Strategically, what I'm really talking about is traffic engineering all of the traffic in your network, running a holistic process to give you optimization. But in many networks, actually what you see is that there are a few very high bandwidth demands, and there are a large number of very much smaller demands. So it might be that actually a more effective process in your network is to look at tactical optimization. That is just optimizing for those few very high bandwidth demands, and that may give you a simpler approach. Then how often to re-optimize? I think it's quite interesting when you look at some of the router-based approaches for re-optimization, the time-based approaches for re-optimization, that they're often based upon the preceding time window, the last hour. But actually the last hour is never generally a good indication for the next hour. So you might find that I've just had my peak, I increase my rate, I increase my tunnel bandwidth, but I'm just coming out of the peak, so I actually need less now, and I actually needed more an hour before I was doing my re-optimization. But also, if we were saying that you've got a few very high bandwidth demands, those high bandwidth demands tend to fluctuate less in time. So again, it might not be that you really want to re-optimize on a sort of 5-minute granularity, but actually, it might be more sensible to re-optimize over time periods of days and so on. And then if you choose MPLS TE, you've got another set of questions you need to answer. Are you engineering all the traffic? Is it a core mesh? Is it an inner mesh? Are you going to statically define the tunnels at the head ends? Are you going to allow the head ends to calculate their own tunnel paths? How are you going to set the tunnel sizing? And now that might sound like a really, obvious. It might sound like there's a really obvious answer to that question, but actually it's not necessarily the case, because so I set my tunnel to 400 meg because I have a traffic demand of 400 meg. But when is that traffic demand 400 meg? Is that the peak? Well, if it's the peak and you set all your tunnels to the peak, then you're going to reserve bandwidth, which in a lot of cases won't be used. Okay, well, I'm not going to pick the peak. I'm going to pick something less than the peak. Okay, well, then you might find if your peaks line up, you're going to have congestion. So, just a simple question like what size do you want to set the tunnels at is actually perhaps not quite so simple. In terms of the optimization of those tunnels, are you doing that online? Are you doing that offline? Are you calculating that and then setting it to the network? Are you letting the network do its own thing? And then some other issues I've called traffic sloshing, but I can go into that in another session. But these questions, so where this session was titled as Best Practices in Network Planning and Traffic Engineering, I think really what I'd hoped to get in, but not done in the time, is a really much bigger breakdown on those issues and understanding of sort of best practice in those areas. But I'd definitely be happy to do a follow-up session to talk about those in more detail. So, next, we've potentially done some optimization. It's an optional step, but maybe something that you want to do to get most efficiency from the network. You're going to then end up with a set of capacity requirements, have to deal with the problem of network provisioning. But to finish off with, my PC will wake up. It's obviously going to wake up and go to the end of the presentation now. At last. There we go. So to finish up with, I started off by saying trend that we're seeing is a breakdown between these boundaries of what were previously silos of planning, engineering, engineering and operations. Okay, well, you might see that it makes sense to have this breakdown, but to break down those boundaries between planning and engineering, because whether or not you need to upgrade a link directly relates to engineering, because it might be that you don't want to upgrade that link, you want to in some way change your topology, either logically or physically, in order to cope with that traffic demand. So it may be obvious to see why there shouldn't be these strict boundaries between planning and engineering. But what about operations? How does this relate to operations? Well, this is one example that that I'm using to try and illustrate the idea. So here we're showing in the top half of this, we're showing the utilization on a number of links plotted over time. And then effectively what you can see between the light grey is actually what's happening, and the dark grey is a future prediction in time. And along the bottom axis we've got hours, so you can see we're going from 10 o'clock at night through to 10 o'clock at night, so this represents 24 hours. So in the bottom, if you may be able to just about see it, there's a red dash which is an interface going down. And when that interface has gone down, you can see that what we get is a traffic increase on a number of links. Okay. But that traffic increase on a number of links, but you can see they're all still below 50%. Am I too worried? Well, what the right-hand side represents then is taking the previous 24 hours traffic profiles and simulating them on the network topology as it is after that link failure at, 2 o'clock in the morning. And so what you can see is that, actually as we go through the day, I don't have much of an issue with that link failure. But when I get to around 1 o'clock, where I'm starting to get up into my peak, you can see that then if the traffic profile I had yesterday is the same as the traffic profile I'm going to have today, I'm actually going to hit congestion. And so from an operational perspective, that's actually quite an important piece of information, because now I know that I've either got to fix that problem, that link has got to be fixed within that time, or if not, I've got to take some other action in order to try and stop getting into that space. And that other action could be perhaps a bit of tactical traffic engineering to route some traffic over another path, or some other potential approach. So this was aimed to try and show, to try and illustrate the point that when we look at network planning, which is essential to ensuring you can deliver your SLA targets, really these silos of planning, engineering and operations are somewhat breaking down. Okay, I think I'm 1 minute over time, which isn't bad for me. I know that was probably quite a lot for first thing after the party, but if there's any questions, I'll be happy to take them. And I'll be around certainly for the rest of the morning, so if anybody wants to discuss any of this, be happy to have a chat. Any questions? Yeah.
One comment to this last slide. You said you're going to take the last 24 hours for the prediction. Right? I would say you'd rather take the 7 days
Absolutely.
ago for a week ago, because we see a lot of differences between, for instance, Saturday and Sunday.
Absolutely. So you're right, and it was an example.
Yeah. And then I would like to make a general comment. I like the academic approach of your tool. However, if there is no money around, then you can predict traffic jams, etc. Well, I don't want to mention a name, but we see that some networks don't upgrade, even though they should have done it 12 months ago.
Yeah. So just on your first point, you're absolutely right. And it was an example, and I think you can take, I think what you might want to do is take yesterday's traffic and compare that with a week ago's traffic, and compare that with a month ago's traffic, because typically we see different peaks at different times of, on different days, but also different months. Certainly, in the UK, as you get towards the end of the month, you start to see an increase in traffic. Interestingly, in the US, the traffic peak, I think, tends to be something midweek. In the UK, I think it tends to be the weekend. So you get splits on those. But I think if you're doing this as an online process and you have those snapshots, it's very easy to then select which of those you might want to do an overlay on it. But yeah, absolutely agree. On the second point, if somebody who doesn't want to put any more capacity in, there's not much help we can give to them. Yes, yes, yes. Perhaps now they know the consequence of not upgrading. Yeah. And maybe your and maybe your intelligent decision is to say, I'm going to upgrade when my links reach 150%. Okay. Any more questions? No? Okay. Thank you very much.
Agno. Hi, Agno.